Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Right, let's have a look at the 2013 question, and it was 9 on paper 1 on sequence and series. Shapes in the form of small equilateral triangles can be made using matchsticks of equal length. These shapes can be put together into patterns. The beginning of a sequence of these patterns is shown below. So triangle 1, so you can see this is what we would call T1, term 1, term 2, term 3, and it says draw the fourth pattern in the sequence. Okay. Drawing is not my forte by any means, but anyway, let's give it a bash. Let's ignore the bits at the bottom. Okay. Okay, I think that's okay. All right. So this is the fourth pattern. All right, the table below shows the number of small triangles in each pattern and the number of matchsticks needed to create each pattern. Complete the table. Okay, so in the first one, I can see the number of small triangles is 1 and the number of matchsticks required was 3. In 2, I can see 1, 2, 3, 4 small triangles. And the number of matchsticks needed was 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And the third one, the number of triangles is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. The number of matchsticks, 3, 6, 9, 12, 15, 18. Okay. And in the fourth one, the number of triangles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The number of matchsticks needed, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, complete the table. Write an expression in n for the number of triangles in the nth pattern. Okay, so the number of triangles, you have to figure out what type of a sequence is it. So the number of triangles is 1, 4, 9, 16. Okay, so I'm adding on the same amount every time, or I'm adding on a number of triangles every time. Okay, so let's have a look. Let's look at the difference, okay, if you remember our common difference. So I'm looking at the difference between the numbers. So the difference between 1 and 4, I added on 3. Here I added on 5. Here I added on 7. Okay, so this is what we call the first difference. And it's not the same, so therefore we don't regard it, it's not what we call a linear arithmetic sequence. Okay, so then we go on to look at the second difference, or the difference of the differences. Okay, so between 3 and 5, it's 2, and between 5 and 7, it's 2. Okay, and that's what we call the second difference. Okay, and we can see that the second difference is the same. So the second difference is the same. Therefore, it's what we call a quadratic sequence. Okay. So like any other quadratic, if you remember a normal quadratic, we would say any quadratic is the form ax squared plus bx plus c. Okay. For sequence and series, though, we tend to use the letter n instead of x. Okay. So from that, though, it's the same as the quadratic you already know. The general term in a quadratic sequence is what we call an squared plus bn plus c. Okay, there's a little bit of theory you need to know in that 2a is equal to the second difference. Okay, our second difference was 2. So 2a is equal to 2, therefore a is equal to 1. Okay, and that's how you get the a coefficient for sequence and series. You get it from the second difference. Okay, I'm just going to insert the page now. Okay, so we have figured out that a is equal to 1. We have figured out that it's a quadratic sequence, so that's my general term. I've subbed in the a being equal to 1 in here and got a tn being equal to n squared plus bn plus c. Okay, the question asked me to write an expression. Okay, so I need to figure out what b and c are. I have two unknowns, so therefore you're looking at a set of simultaneous equations in b and c. Okay, so you have knowledge about the sequence. You know that the sequence is 1, 4, 9, and 16. Okay, 1, 4, 9, and 16. We know that, and dot, dot, dot. Okay, so this is T1, this is T2, this is T3, and this is T4. Okay, so you can say then that you know this is the general form of a quadratic sequence. You can say that T1 would be equal to, so I'm literally replacing n with 1. So I'm going to replace n with 1 all the way across, would be 1 squared, I'll write that in black, 1 squared plus b times 1 plus c. Okay, and we know that's equal to the first term of our sequence. We know our first term is 1. So 1 squared is 1, plus b plus c is equal to 1. Bring him over, and I'll get minus 1. B plus c is equal to 1 minus 1, which is 0. So that's my first equation of my quadratic sequence. And then I set up a second equation. Now, I can use any of these terms, okay, because we know what they are. I tend to use the smallest two because it keeps the numbers smaller. That's all. That's the only reason. So the second one I would tend to use is T2. So now I'm replacing n with 2 so that I get n squared, so 2 squared plus b times 2 plus c, and we let that equal to whatever your second term is, which is 4 in this case. 2 2's are 4, plus 2b plus c is equal to 4. Bring over the 4, and I get 2p plus c is equal to 4 minus 4, which is 0. Okay. And then you bring your simultaneous equations together. The simultaneous equations tends to be quite a simple pair. Okay, we are going to cancel the c's. They're the obvious one to cancel because they're the same. So change the signs, and you can change top or bottom. Let's change the top to keep everything positive. So I have minus c plus c is gone. I have 2b minus b is b, and it's equal to 0. Okay, so I figured out b is equal to 0. If you've taken term 1 like we did, you'll have an expression that says b plus c is equal to whatever, 0 in our case. Sub in your 0 here, and we're getting 0 plus c is equal to 0, so c is also equal to 0. Okay, so that means that our general term Tn is equal to, if you remember, it was n squared plus bn plus c. It's then equal to n squared plus 0 times n plus 0. So our general formula is just n squared. Okay, and does that work? Check your answer. So for T1, is my term answer 1 squared? Well, it is. For T2, do I get 2 squared is 4? Yes. T3, 3 squared is 9? Yes. T4, 4 squared is 16. If I asked you to work out T10, you'd be able to tell me it's 10 squared, it's 100. So once you have a general formula, you don't need to draw any more patterns like we were doing here. You can, I suppose, algebraically figure out what all the terms of the sequence is. So that's really important to be able to come up with the general equation for a quadratic sequence. Okay, the question's not done yet. C said, find an expression in n for the number of matchsticks needed to turn the n-1 pattern into the nth pattern. So I want now an expression for the number of matchsticks needed rather than the number of triangles. So I'm going back here to see number of matchsticks. So 3, 9, 18, 30. 3, 9, 18, 30, and so on. And again, I look at the differences to try and establish a pattern. Okay, so 3 to 9 is a difference of 6, 9 to 18 is a difference of 9, 18 to 30 a difference of 12. Okay, it's not a linear arithmetic. First difference is not the same. So let's have a look at the difference of the difference. So we see that the second difference is the same. Therefore, again, it's quadratic, okay? And you're looking at Tn being equal to an squared plus bn plus c. Remember that 2a is equal to the common difference. So our 2a is equal to 3, divide across by 2. So our a is equal to 3 over 2, okay? Not as nice as the last one. I have 3 over 2 n squared plus bn plus c. Okay, and then I set up my T1 and T2 just like I did on the last one. Okay, so again, T1 in this one would be equal to 3 over 2 1 squared plus b times 1 plus c, and my first term is 3. We'll get that here. Okay, so therefore I'll end up with b plus c being equal to 3 minus 3 over 2, which is just 3 over 2 as well. Okay, my T2 then is equal to 3 over 2 by 2 squared plus b times 2 plus c, and that's equal to my second term, which is 9. So I'll have 2b plus c being equal to 9 minus 3 over 2 by 2 squared, which is 4. Okay, so there's your two equations. You bring them together. So b plus c is equal to 3 over 2. 2b plus c is equal to 3. Cancel the c's again. And I get b being equal to 3 minus 3 over 2. So b is 3 over 2 as well. Sub in for c. B plus c is equal to 3 over 2. 3 over 2 plus c is equal to 3 over 2. So c is going to be equal to 0. Okay, so my expression then, if I could write it up here, Tn for this one is equal to uh, 3 over 2 n squared plus, what was my b? 3 over 2 n plus c, and my c was 0. So that's an expression for Tn. Okay, now watch the question. Didn't ask you for an expression for Tn. It asked you for an expression for the number of matchsticks needed to turn the nth minus 1 patron into the nth patron. Okay, so let me add in a page. Sorry. Okay, we'll move him there out of the way. Okay, so I want the number of matchsticks needed for turning the nth patron into the nth minus 1 patron. Okay, so I have an expression now for Tn. I need to find a similar one for Tn minus 1. Okay, so what we say is if Tn is equal to 3 over 2n squared plus 3 over 2n, then Tn minus 1, so just like in functions, you replace your n with your n minus 1, okay, plus 3 over 2n. Okay, so that's 3 over 2 square the first, square the second, twice the product of the two, and then multiply in the 3 over 2 squared minus 3n plus 3 over 2 plus 3 over 2n. And then that's 3 over 2n squared minus 3 over 2n plus 3 over 2. Okay, so now I can take them away like I'm doing up here. So let's take them away. So I have Tn, which is 3 over 2n squared plus 3 over 2n. And I want to minus that 3 over 2n squared minus 3 over 2n plus 3 over 2. Okay, so I'm getting 3 over 2n squared plus 3 over 2n minus 3 over 2n squared plus 3 over 2n minus 3 over 2. He cancels with him. I have 3n there, and I have a minus 3 over 2 there. Okay, so an expression to turn Tn minus 1 into the nth patron. The number of matchsticks in the nth patron in the sequence can be represented by the function un equals an squared plus bn, where a and b is an element of q and n is an element of n. Find the value of a and the value of b. We have it done here. How strange they would ask it again. 3 over 2n squared. There must obviously have been another way of doing that first part that was easier than that. I tend to always do things in the long way. So that's part D done. So you can see our A is 3 over 2 and our B is also 3 over 2. Okay. And then E said, one of the patrons in the sequence has 4, 1, 3, 2 matchsticks. How many small triangles are in the patron? Well, we have to figure out which n we have first for that number of matchsticks. So we have 3 over 2n squared plus 3 over 2n equals to 4134. And my thinking is if I've solved this for n, I'll figure out which term in the sequence I am, and then I can go back to my expression for the number of triangles that represents. Okay, so that's where I'm going. This is looking like a quadratic, so 3/2n squared plus 3/2n minus 4134 is equal to 0. I think I would just do the minus b formula. So x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So I could try simplifying my quadratic. I tend not to bother when I'm using the minus b formula anyway, because your calculator is going to do the work. So why would you take the chance of making a mistake by simplifying it? Okay, well, you might argue that it would make putting it into the calculator easy. And you would be right. Okay, let's try and get this into the calculator. 3/2 all to be squared minus 4 bracket 3/2. Close your bracket, open another 4ac minus 4134. Close your bracket. So I am getting 157.5 for that. Okay, let's split our brackets. So hit the fraction button. On the top one I have minus 3/2 plus 157.5 all over 3, and I'm getting 52. And if I go back and hit minus, I'm getting minus 53. I obviously discard him, okay, because you can't have a minus term in a sequence. So it's the 52nd term, okay? So T52 has 4134 matchsticks. Okay, so therefore, how many triangles? Well, if you remember, the number of triangles was equal to n squared. That's what we worked out the Tn for, the number of triangles. Okay, so therefore T52 is equal to 52 squared. So I'm getting 2704 triangles. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.